Hello. In this video, I'm going to continue with Lab 3. So at this point, you should have the LTspice model built, and you'll be either using these PMOS and NMOS devices that are given, or you will have found a model of your own choosing. And regardless of what model you use, make sure you look up the data sheet. So just to go over quickly a few parameters that you could look up in the data sheet. Looking at my circuit, I went with the 2N7002 and for the NMOS and the ZVP3306A for the PMOS. And the reason I went with these two is I was very familiar with the 2N7000, and after trying to get a suitable model to work on LTspice, I was able to get the 2N7002 to work, and I found out that the 2N7000 comes in the TO92 package, so it looks like a transistor. The 2N7002 is a surface mount device, but they're pretty much the same exact component. And then I was not familiar with the ZVP3306A, so I did a little bit of research trying to find a suitable PMOS to use in the circuit. And let me pull up the data sheet just to give you an overview of what I looked at. So this is the 2N7000, and you can see here that the drain to source breakdown voltage has a minimum of 60 volts, and the resistance between the drain and the source when the device is fully conducting is 5 ohms. And then the drain current, the maximum drain current, you can see down here, is 200 milliamps when current is flowing continuously. And then the power dissipation of the device is 1 watt. So looking at the PMOS, the drain to source voltage, we're getting negative 60 volts, which is comparable to the 2N7000. The continuous drain current, we're getting negative 160 milliamps, which is a little lower than the 200 milliamps that we got from the 2N7000, but it's pretty close. And the resistance between the drain and source when the transistor is fully conducting is 14 ohms, which is slightly higher than the 2N7000. And the power dissipation of the PMOS device is 625 milliwatts, so it's slightly less than the 2N7000. So those are just a few parameters that you could look up when you're trying to compare your devices and trying to get a suitable match. Going back to the lab manual. So we're going to verify your circuit's operation. We're going to use a transient analysis and make sure that the gain is 10, and then you're going to do an AC analysis. You're going to do a maximum input voltage, so you're going to determine what your maximum peak to peak is before saturation, and you're going to create a parameter sweep to determine the value of the minimum value of the load. So see how heavy a load it can drive. We've done all these in the past, so there's one item I wanted to talk about with the minimum load, and let's go ahead and do that. So you can see that I'm using a cascode current mirror. I would refer to chapter 9 in your workbook activities, because there's different current mirrors you can use. There's even a cascode active load you could try with your design just to make it a little bit different than the given values. So I'm going to run this, and you can see the load I'm using is 100K. So I run it, I'm getting an output of 1 volt peak, and the input I'm sending in is 100 millivolts peak. So let's do a step parameter just to try to get a ballpark of how large of a load we can drive. Okay. So let's go from 500 to 10,000, and let's do it in 100 ohm increments. And we'll run it. There we go. And so we can see that it starts to saturate. You see these flat spots on the bottom? That's the signal starting to saturate. So what we could do, so it starts at 500, and then it stops at 10K. And it looks like we have 1, 2, 3, 4. So what I'm looking at is this is the 500 ohm load, 600 ohm load, 700 ohm load, 800, and then this like pink looking one would probably be the 900. So let's just do 900, and we know 1000 works, so let's look at that, and instead of doing it by 100, let's do it by 10. It's not as bad. Let's also change the time step to, let's do 2, so we're able to zoom in a little bit. There we go. Let's drop this down a little bit to 800. So I'm just trying to find where that, oh yeah, there it is. So that's saturation, so 800. So when we were at 900, we didn't get it saturating like that. So maybe we could do 850 and run it. And so it still saturates at 850. So these are just some techniques on how you can find that minimum load value. So I think the main thing to point out is a load of 890 ohms is not a very heavy load. If you think about an amplifier driving a speaker is usually 8 ohms, which is extremely low. And if we were to drive 8 ohms with this, it would look really ugly. It would just saturate, so you would just hear crackling and distortion coming out of the speaker. So what I wanted to do was to show you how to increase the linear range to help drive a heavier load. And looking at the workbook activities, section 9.6 talks about this. So I would refer to 9.6, but I'm just going to show you how to obtain the graph in LTspice. Okay, so we're going to go back here and we're going to rem that out. We're going to change the load back to, let's just change it to 850. And, sorry, actually, let's change it a little higher just to make sure we get a good graph when we're doing this in the beginning. Okay, I'm going to zoom in so you can see what I'm doing. Okay, so we want to pull up this, and so to do that, all I did was right click on my mouse, and we're going to go to DC sweep. And so name of first source to sweep, we're going to sweep the input, so V1. We're going to do a linear sweep, and we're going to make our start value -8, and let's make our stop value at 4, and increment 1 volt at a time. Okay, and we don't want it to be a sine wave, so we're going to press none, and we could set the DC value to 1. Okay, so now we're going to run this, and we're going to look at the differential pair, and we want to see when the source and drain turn on. So you can see when one turns on, the other goes negative, and so then we do that on both sides. Okay, and so this is what I wanted to point out, is this region where it's sloping is the active region. And the longer we can make that active region, the larger load we can drive. So there's a couple ways to do that. You could either increase the overvoltage to extend the linear region, which we're not really able to do that with this design, or we can increase the bias current to increase the gain. So that's what we can do, and you can see this linear region's about 1 volt, and this one's about 1 volt, from -6 to -5, from 0 to 1. And so to increase the bias, we can decrease our reference. So this is going to change our current, right? Right now we're at about 1 milliamp. So it's going to increase that. But remember, we looked at the data sheet of those devices. And what was the maximum drain current? It was 200 milliamps for one. For the 2N7000, it was negative 160 milliamps for the PMOS. So if we set this at 100, you see how now we're at -6 to -4, and we're from 0 to 2. And so that's our linear region, and our new drain, or our new bias current, is a little, like right around 100 milliamps. I think it's like 95 milliamps. So keeping that in mind, if you were to do this experimentally and you were using a 100 ohm resistor, you'd have to keep in mind of the wattage rating. Okay, so now that we've changed that, now let's look at how heavy of a load we can drive. So now I have to change this back. We're going to go to advanced, go to sine, 0. I was doing a 0.1 volt amplitude at 1 kilohertz, and we're going to do a transient analysis. Okay, so at 10K, we get a good signal. Now let's do a step parameter. Let's go from 500. We weren't able to achieve 500 before. Let's see if we can get it now. Oh yeah, that looks a lot better. Let's see how low we can go. Okay, so we're able to get down to 100. Let's see if we could drive an 8 ohm speaker. So not quite an 8 ohm speaker, but you could do a 16 ohm speaker. Yep, you could do a 16 ohm speaker. So again, that section is in your workbook activity, chapter 9.6, and it goes over extending the active region. And we did that by increasing the gain, the bias current. And I just want you to observe for lab 3, there is no requirement to have a 1 milliamp current. I know in lab 2 we had a requirement for 1 milliamp current, but this one you don't. So give that a shot and see if it helps your design drive a heavier load. Thank you.